My brother gets a jacuzzi and tells everybody to come over and jump in. I'm like, summer?
Mhm.
Oh,
Any other time would be nice.
I'm like, yeah. Don't you get like non-pandemic, you know?
How's it going, Professor?
Yep. Did someone call me?
Oh, sure.
Oh, hey.
How's your day so far, Dr. Tran?
It's been good. It's good to be back. I had 2 in-person lectures yesterday, and so I think a mix of like anxiety, but also kind of, just generally nice to be back. So, we'll see how the semester goes, and then we'll go from there. But overall, it's been good.
That's cool to hear.
How about you?
It's all right. Not too bad. Had senior design in the morning and then some gym. And then, well, here I am. I was planning on going in person, but kind of want to test the waters online before I head over in person.
Sounds good.
Saves me the commute too.
For sure, for sure. That was trippy for the first few exchanges. I thought that was someone in the classroom, but the speakers are like somewhere out here. So the sound's not coming out of my laptop, so it's kind of tripped me out for a little bit.
Oh wow! So you got Dolby surround sound in there?
I guess so. Some kind of surround sound.
That's cool.
Hi, Chris.
What's up, Steve?
Right. We're gonna do theory behind FDA today, so it should be lecture notes 01, I think.
Oh,
Yep.
is it okay if I take off my mask and put my glasses on?
Oh yeah. For short things like that, it's okay.
Okay.
Yes. Yep. Wait a second. Yes, yeah, this computer should already have the software.
Josh is coming in. I'll be done with the lights all white. Huh? And I'll be done with the lights all white. And all the right places. You're behind me. Now I can't, I can't use it without being plugged in. I blame you completely. Is that? That's not that I see. Yeah. Okay, like put in that thing, like run that thing. It's not plugged in, right? See if it's for you. I would never do it. He almost kicked us out at like 5:15.
Yeah, I know. He
Oh, did he find you?
yeah, he called me. He said, "Are those your students?" I'm like, "Yeah, those are my students. You can leave them in there. It's fine."
He said, "Oh, really? You have someone in here?" I'm like, "Yeah, no worries."
I think he's confused because last week he didn't meet in person. So I think I
Right.
checked here last week, no one was here, and then now you guys are here.
Or you just have a community. I can hear you. Yeah. Yeah. Hey, what's your name? I'm Colin. I'm sorry, yeah.
No worries.
It's always one of those things, it's like, "Oh, it's so polite. I know, right? Not shake your hand." We had, remember had a meeting with all the other day. I wanted to shake the hand. It's pretty good, you know. Don't. I felt so awkward. I was like, yeah. Really, I like the game, but it's intense. Not that is.
I think they didn't come to you.
Oh, did you? Yeah. Thanks. I wanted to- Yeah.
I don't know if
I think that's nice.
school.
All right, 5:30. So let's go ahead and get started today. All right, good evening, everyone. How's everyone doing? So good to see everyone here. It's you know, I know it's the first time we're meeting in person, so it's really nice to see all of you. Especially, I know some of you I've had in my classes over the past year, and so it's really nice to finally see what you look like in person. So it's been kind of a weird year, but it's good to be back. And so I know it's a little bit it's a little bit uneasy still, but hopefully we'll still have a good year. Okay? And so welcome everyone on Zoom too. So if you guys can't really tell, I've set up like my laptop here in the classroom, and so I'll be streaming this on Zoom, just like I always do, but I'll be physically here in the classroom. But I tried this out yesterday, and this kind of seemed like the best kind of setup for having both people attend virtually and have people here in person as well. Okay. All right, and so today we're going to be continuing on with finite elements. Okay, and so today, I thought I'd take an opportunity to talk a little bit about some of the theory behind FEA. Okay? And so we're not going to do too much of that in this class because I do want this class to focus a lot more on the practical applications of FDA. But I think we do still need to have a little bit of theory, just so that we have kind of a full holistic understanding of what we're using in the software. Okay. All right, and so before we begin, are there any questions I can answer before we get started? Okay. Yeah.
I was trying to figure out where to watch the recordings.
Oh yeah, sure. Yeah, I can show you real quick. So I think the best way to do that is from the course website, and so I can show you here. So people on Zoom, you can't see this, but everyone here in the classroom can. And so if you go to the homepage of our course website here on Canvas, you have access to the Canvas site?
Yeah.
All right, and so if you go to the bottom here, so you see where it says a course outline. And so if you click on the week of the lecture that you want to view, so go ahead and click on that week. And then you can see here, there's links here to go watch the recorded lectures. And so if you click on the link, it'll take you straight to YouTube. And then if you look at my YouTube profile, I also have playlists. And so there's a playlist for EGME 410. And so all the lectures will be on that playlist. And then actually last year too, all the lectures from last year are on that playlist as well. Yeah, we're taking a little bit of a different trajectory this year. So don't pre-watch all the lectures from last year and expect to get the same thing this year, because it's I am changing things up quite a bit in this class. But if you're interested, you can watch there too. Okay. Okay. Oh, actually, let me tell you guys a funny story before we begin. It's so over the weekend, I went to my first wedding ever since COVID began. It was for my fiance's friend actually, and so it was kind of a big event, but everyone was wearing masks, so it's okay. But it was funny because their family is kind of a traditional kind of like a Christian family, and so my fiance and I, we live together, and so to them they when two people kind of live together, it's kind of like they're already married. And so when they sent us the invitation, they already called us Mr. and Mrs. Justin Tran. And then at the wedding, they our nameplate said Justin Tran, and then my fiance's name is Jen, said Jen Tran as well. So it was funny because like we got to the event, it's like, hey, we got married today. Whoa. Same day as your friend's wedding. It was kind of a funny thing. But
Like, are you trying to tell me something?
yeah, we can save a lot of money on the wedding. That'd be really nice. But yeah, it's kind of a funny thing that happened over the weekend. Okay, so let's go ahead and get started. And for you guys on Zoom and for you guys in the classroom too, if the audio's kind of strange or you guys can't really hear me, just don't be afraid to let me know, because it's I didn't have any issues yesterday, but I know every day is a little bit different. So just let me know if you can't hear anything or have trouble seeing anything that I'm doing. Okay. Okay, so let's go ahead and get started. And so the subject for today is going to be theory behind FEA. Okay. Right, and so I call these lecture notes theory behind FEA, and they're relatively short. And so they're only going to take us a day to cover it, hopefully. But in reality, this is a subject that I like talking about a lot. And so usually my other finite element classes, I usually dedicate the entire semester to this, just because there's so much to go through. But just kind of based on the feedback that I've gotten from this class, I want to focus a lot more on the application. But we should still talk about a little bit of theory just to make sure that none of that is completely lost. Okay. All right. And so the first thing I want to say is that, you know, I think typically when people think of finite elements, they think of softwares like ANSYS, you know, Abacus and SolidWorks, right? And so they make this association that finite elements is like a computer thing. It's a software. But actually, you know, finite elements doesn't really have anything to do with computers at all, right? Okay. And actually, if you look at the historical development of finite elements, it actually was developed kind of way before computers actually really became a thing, right? And so all finite elements is it's basically just a method to go from a differential equation. It can be an ordinary differential equation or a partial differential equation, and then it transforms that into an algebraic set of equations. Okay. Okay. And so as an example here, let's have the heat equation. And so the heat equation is, you know, one of the differential equations we see a lot in engineering. Okay. Okay. And so here we have it's a partial differential equation. So we have a PDE. Okay. Right. And so through finite elements, what this will do is it'll take this complicated differential equation here and turn it into a system of algebraic equations, right? And so if you remember from linear algebra, you know, if you have a system of linear equations, the way that we commonly like to represent this is as a matrix set of equations, right? And so let's say that we have a matrix A, some solution vector X, okay? And this is equal to some right-hand side vector B, okay? Right? And so when people were first developing finite elements, they said, you know, differential equations are really, really hard to do. And so if we can transform them into a different form, but still get kind of the same answer or a very similar answer, then that will be, then that's a good thing. Then that'll help kind of reduce the complexity of the problem. Okay. The problem with this, and kind of the reason why finite elements didn't really take off for a long time, is that this set of algebraic equations here is they're, you know, if you want to use this for anything practical, these algebraic equations are absurdly big. And so you're talking about, you know, like if you think about back to your linear algebra class, right? I think people generally started complaining when you had to solve anything bigger than like a 3x3, right? And so we have 4 equations, 4 unknowns, then it kind of becomes kind of a bitch to solve. But you know, for these finite element problems, what you're talking about here is like something on the order of like thousands, right? And so even like a very modest finite element problem, you can get a linear system that's like 10,000 by 10,000, right? And so you're talking about like 10,000 equations by 10,000 unknowns, which is, you know, kind of absurd to do by hand. And so before computers came out, you know, people kind of presented this finite element framework, and then everyone just kind of made fun of them because it's like, you know, this is useless to us. Like solving a 10,000 by 10,000 system is, you know, just as hard or even harder than solving like a differential equation, right? And so it really wasn't until computers started becoming, you know, more and more powerful that this actually became, you know, something useful. Because one thing a computer is really, really good at, a computer is really, really good at doing algebra, right? Okay. a computer can't really handle a differential equation just by itself. And so in order for a computer to solve a differential equation, you kind of first have to transform it into an algebra problem, right? And then once you get into an algebra problem, then the computer can really take it from there, right? And so, it wasn't until, computers started to become more powerful, people actually started developing algorithms for solving algebraic equations on the computer, that people realized that, hey, that guy we made fun of 50 years ago, I think maybe he was onto something. We can actually use this for something useful, okay? And so this is kind of the development of how finite elements kind of became, as we see it today, it's kind of like a computer thing, because without computers, finite elements is actually not that useful, because you end up with these absurdly big algebraic systems of equations that you can't really solve by hand. Okay, so any questions on this so far? Okay. All right. And so that's how finite elements kind of became a computer thing. And so, at what point in history did finite elements kind of start to become an engineering thing, right? And so we talked about on the last page that finite elements can take a differential equation and transform it into an algebraic system that a computer can solve, right? And so it just so happens that a lot of engineering systems of interest, their behavior is governed by differential equations. Okay. And so on the last page, I showed you the heat equation, right? And so the heat equation is a partial differential equation. If you do any kind of thermal engineering, you're going to be working with heat equation to some degree, right? Like the ones that we'll use a lot in this class is the structural mechanics equations, right? And so that's another partial differential equation, because that relates, stress and strain within a material. Okay. And so since you have all of these kind of engineering systems that are governed by differential equations, it kind of makes a lot of sense to kind of partner this up with some finite element software, right? And so kind of the flow chart the flow chart of logic of how you get from like a physical engineering problem to finite element results kind of goes something like this, right? And so let's start with a physical engineering system. Okay, and so this is probably a system that you're looking to analyze or you're looking to design. Okay, so this could be like your bridge, or it could be like an airplane, could be like a vehicle, right? Okay. And then from this physical engineering system, what you can do is you can ask yourself, what are the differential equations that govern its behavior? Okay, and so here we get governing differential equations. Okay. And so depending on the type of physics that you expect there, that you can get those equations. From those differential equations, you can then use finite elements. Okay, so this is where FEA comes in. Okay. You can use finite elements to transform this into a system of algebraic equations. Okay. Right. Now that you have the problem set up as a algebraic problem, you can use a computer to solve this. Okay, computers are really good at this. And so from here, what you're going to get is a solution to the algebraic equations. Okay. Right. And so from here, all you have from here are just kind of a raw solution. And so if you think of it, it's kind of just a list of a bunch of values or a bunch of numbers. That's the solution of your linear system. And so you have to do a little bit more here. And so at this point, we use a step called post-processing. Okay. Okay. And at this point, this is when the results are put into a form that's usually useful to you, right? And so if you think back to our ANSYS activity from last week, we were looking at distributions of the deformation of the equivalent stress, right? And so that's usually when that's usually what post-processing does, okay? And then from here, this is when you start to do your engineering work, right? And so if you use your finite element solution to perform design or maybe to perform analysis, right? And so this is when you would take your engineering results and or take the finite element results and apply it back to your physical engineering problem. Okay. And so that's kind of the flow chart of logic of how you go from like a physical engineering problem that you would encounter professionally or from your student projects, and then taking it through the finite element process to something that you can actually use. Okay? And in terms of what ANSYS actually does for you, all right. And so ANSYS does a little bit more than just this computers part, right? And so I know I have that part there for computers, so that's when the computers do most of the work. But ANSYS as a software kind of handles a lot of this for you. And so, actually, if I could box all of these parts, okay, ANSYS is doing basically all of these things for you, right? And so all you have to do, as an engineer that's using ANSYS is to come to ANSYS with a physical problem. You have to know how to input that into ANSYS. And then ANSYS is going to handle kind of all this stuff that's kind of in between, okay? Because I think most users, of the software, and you guys can kind of speak to this too, because last week you guys used it for the first time, you weren't really aware of all the stuff that's happening in the blue box, right? Because that's because ANSYS kind of handles all that for you, kind of under the hood, and it presents it in kind of a very nice user-friendly package. And I'm using ANSYS as an example here, but that's not the only one that's out there. And so if you think of like Abacus or SolidWorks simulation, they're going to be doing the same thing. And so, the goal for any kind of front end, user software is to kind of package all that stuff in the blue box and kind of make it almost invisible to the user. But underneath the hood, that's kind of what's going on. Okay? And so today, what I want to do is I want to go through a little bit of what's going on in the blue box. Just so that you guys are a little bit more aware of what's going on underneath. Okay, so any questions on this? Okay. All right. And so before I move on, I do want to say that even though a lot of times we use finite elements to work on physical problems, finite elements is not just limited to that. And so if you take any differential equation, in theory, you can apply finite elements to that as well, okay? And so, for us, it doesn't really, that feature doesn't really come into effect because, as engineers, most of the time we work with, physical systems. But actually, you'd be surprised that a lot of like mathematicians and applied math people, they use finite elements to look for solutions to their weird esoteric math problems that they like to do for some reason. But yeah, so it even has a lot of finite elements has kind of reached pretty far and wide at this point. But I think for the most part, most people that use it are engineers like us. Okay. Okay, and so the next thing I want to talk about is what a boundary value problem is, because this is kind of the basis of how do you actually set up a problem such that finite elements can actually handle it. Okay. And so the definition of a boundary value problem is that it's a mathematical expression of the type of problem finite elements can solve. Okay. All right. And so, intuitively, what I like to think of boundary value problems, even though the general definition is more, general than this, but I like to think of this as kind of just a simple physical situation with real physics and a physical boundary. Okay. And so that's kind of the requirements that you need in order to perform a finite element. Okay. And the reason I'm going through this, it kind of seems like kind of an abstract math thing, is that if you think about your finite element problems in terms of what the corresponding boundary value problem is, it really kind of makes your analysis a lot simpler, and you're going to be able to define things a lot more easily in that sense. Okay. Okay. Because what we're going to go over is that, boundary value problems have three kind of main aspects, or three characteristics. Okay. And if you think about your physical problems in terms of these three characteristics, you've kind of already done most of the battle of, how do I input this thing into ANSYS? Okay. All right. And so let's talk about those three components. Okay. Okay. And so the first component is the domain. Okay. And so the domain is basically, this basically sets the geometry, or sets, the where and what you want to solve your finite elements on. Okay. And so most of the time, if you're doing a finite element analysis, this is kind of the very first thing that you have to specify, right? If we think back to our activity last week, and so our domain for that activity was simply just the rectangular plate with the hole, right? So remember, the first thing that we did in the activity was we basically went into the CAD software, we CAD'd it up, and then from there, we were able to do everything else. Okay? And so before you do anything in finite elements, you need to have some geometry that you're specifying. Okay. All right. And so for everything that we're going to do in this class, the domain usually consists of some kind of CAD file, either something that you're creating, right there on the spot within ANSYS, or something that you're importing from another software. Okay. Okay. All right. And so let me give you some terminology of how people usually refer to domains. Okay. And so here I have an amorphous blob, right? And so let's say that amorphous blob is what we want to solve finite elements on. Okay. We use this simple omega. My stylus would stop freaking out. Come on. There we go. Okay. And we use this symbol omega here to denote the interior of the domain. Okay. And so that's going to be separate from the outer boundary of the domain. Okay. Okay. And so for the boundary of the domain, we usually give this the symbol partial omega. Okay. So these are kind of the two regions that I want you guys to keep in mind. Okay. Mostly just because, you know, the boundary is something that's going to be important, because that's where we're going to apply our boundary conditions. And so things like our loads and supports and constraints. So that's going to be applied in the on the boundary. Okay. All right. So any questions on this so far? Okay. All right. And so the boundary seems pretty straightforward, but there's a lot of important questions I want you guys to think about, you know, when you're setting your boundary. Okay. Or when you're setting your domain. Because I'll tell you that the common temptation that a lot of people have, you know, especially once they get out into the workforce, is to take a CAD file and just, you know, spit that up into ANSYS kind of right away. Okay. In a lot of cases, that's fine. You know, that'll be okay. But, you know, a lot of times these CAD files are created for, you know, different purposes other than finite elements, right? So a lot of times you're creating a CAD file to give to a machinist in order to make a part. Maybe you're making CAD file to make a rendering for, you know, an entire, you know, setting or something like that. Okay. A lot of times these CAD files are either a lot more sophisticated or they have a lot more features than what you need for the finite elements. Okay. Okay. And so I'll give you a couple examples here. Okay. Right. And so this first example actually comes from a previous time I taught this class. I think it was maybe 2 years ago. And so someone, for their final project for 410, you want to do a finite element analysis of a bench press. Okay. Okay. And so what he did was that he went on to GravCAD and he found a CAD model that someone made of an entire bench press setup, right? And so they had the bench, they had the rack, they had the bar, they had the weights and everything. Okay. Okay. It was a nice looking CAD. I think, you know, whoever did it did a really nice job. But, you know, it was a little bit way too much for what he needed for this analysis. Okay. Because what he was interested in was that, you know, he was interested in seeing, you know, how much weight can he put on the bar and still not have it break, right? Because that was really the only thing that was in danger of failing in that whole setup, right? And so, you know, the first time that he actually ran his analysis, right? So he meshed up this entire, you know, bench press setup, all the racks and weights and everything, and he found that the entire solution was like zero stress. There's no stress anywhere. Okay? The only place where he had any kind of significant stress was kind of inside the bars, kind of where the weights were. Okay. And so, you know, he showed me those results, and I told him that, you know, a lot of this geometry here, a lot of this mesh is kind of going to waste because you're not really doing anything useful to it. Okay. And so it would have been a lot better if you just made a CAD model of just the bar and the supports on the bar along with the weights, right? And so you didn't have all the racks or the bench or anything like that. Because then that would have saved him a lot of time. It would have saved him a lot of trouble to do that. Okay? And so when you're defining your domain for your finite elements, you have to ask yourself, or you should ask yourself, you know, what areas here am I most interested in seeing, or what areas am I going to have the most interesting behavior, and maybe try to formulate your CAD or formulate your geometry around those areas to kind of save yourself a lot of trouble. Okay.
Yeah, that's the funny thing. That was my 421 project,
Mhm.
and I had to learn that the hard way. So
Ah.
I drew it all up, and then we used the simulations in SolidWorks to figure it out.
Yeah, yeah. Everyone in the class is having the same sensation I had earlier, where it sounds like someone in the class is talking, but it's through the speakers that I still don't really know where they are. But
Disembodied godlike voice.
you are a ghost in this room. All right, and so I'll tell you another common mistake with the domain that people often make is that they often include details that are a little bit too fine. Okay. And so a good example of this was one that I had last year. Was a group that was interested in looking at a finite element analysis of tires on a car. Okay. And so, I think everyone here has seen a tire on a car, right? And so a tire has all those, little ridges inside the tire that kind of help with the friction and help with the performance of the tire. Okay. Okay. And so, what you'll see, as we get along later in the semester, that whenever you have these little tiny features in the geometry, those become a pain in the ass to mesh, because in order to properly mesh those fine details, your elements need to be small enough in order to actually mesh them. And so if you have lots of these fine details, your mesh will just kind of naturally really blow up. Okay. Okay. And so what he ended up having to do was he had to go in and go into his CAD file and suppress actually all those little ridges that he had on the tires, which he was very sad to do, because he spent a lot of time actually making those, imprinting those into the tire. But otherwise we couldn't get the simulation to run with that. And so just another factor to consider. Okay. And so this is kind of just a flavor, and so we'll be going through a lot of these issues kind of later on in the semester. But I just want to illustrate to you guys that choosing your domain and really spending some time to think about what are the features that I actually really need, and what are the ones that would make a good finite elements. It's a really important decision, and it's something that people even professionals struggle with a lot. Okay. Okay, so any questions on this?
I actually have a question about the geometry.
Yeah.
Can I just do on like Earth surfaces, like something like pipe or something?
Yeah, you can do that. Yeah, curved surfaces are no problem. It's ones where you get into like really tiny details that are on the order of like millimeters. That's when things get really difficult. But as long as it's a large curve, it's totally fine. Okay, question?
So something that has
Yeah, no, it's a good question. And so there's multiple levels that you can do. And so if you're interested in kind of what's the overall performance of the whole tire, you can suppress a lot of those small features and kind of just do that analysis. But a lot of times you're actually interested in how do these ridges actually behave, and how are they going to wear down as the car goes along. And so in those cases you can do what I call it like a subsystem analysis, where you kind of zoom in on just kind of a small part of the tire, and then just do something like that. And so you don't do the whole tire with all the ridges. You make kind of a small patch with some ridges on that, and then kind of you kind of reform the boundary conditions on that such that you can get those kind of results too. And so yeah, there's multiple levels that you can do, but fine details is a difficult thing normally to do with finite elements. Question? Mm-hmm. Yeah, no, you can do that too. Yeah, there's lots of clever ways that you can kind of get rid of that stuff. And sometimes it's trial and error too, because like the bench press one is a little bit obvious, but sometimes you run a finite elements and then you'll see that a bunch of the geometry just doesn't have any stress at all. And so at that point, you can kind of eliminate it there and kind of refocus your analysis on the other parts too. Was there one more question in the back? Okay. All right, and so that's the first part of a boundary value problem. Okay. And so the next part of the boundary value problem is the governing equations. All right, and so once the geometry is established in your problem, the next thing to define is what kind of physics or what kind of physical things do you expect to happen? Okay. Okay. All right, with the emphasis here on physics. Okay. And so, in ANSYS, the way that you select this is that you select, what type of analysis system that you want to do. Okay. And so if you remember at the beginning of the activity that we did on Thursday, we selected static structural. Right? Okay. And so that tells ANSYS that we're interested in solving a structural problem. Okay. And so once you do that, then ANSYS is like, all right, let me prep all of these structural equations, the structural differential equations for me to solve. Okay. And so if you want to do a thermal analysis, you would do like a steady state thermal. Okay. If you want to do a fluid analysis, you would do fluids. Okay. And so you want to make sure that you choose the right physics for your situation. Which might seem like it's like geometry. It might seem like an obvious thing to choose the right physics, but I've made the mistake before where I've made really obvious mistakes where I specify a thermal system when I wanted to solve like a fluid system. Okay, and so you want to make sure that you choose the right one, but there's some nuance in here too. Okay, because one thing that we'll go over in a little bit is that there's not just one structural equation that covers, absolutely everything. Okay. There's different variations and there's different adjustments based on, what type of behavior that you want to see. Okay. And so as an example, one thing that we'll go over later in this class is if you have any plastic deformation. Okay. And actually, I don't remember if it was this class or if it was 540, but I think some people were kind of experimenting with it too, right? And so in ANSYS, there's a toggle that you can do where you can say that I expect some large deformations to occur, okay? And so if you expect some large deformations, you need to kind of turn that feature on in ANSYS, okay? Because as you guys probably know that, if you're considering just elastic deformation or plastic deformation, then the behavior kind of changes a little bit. And so you need to make sure that the equations are equipped to handle those kinds of situations. Okay. All right. And so another example where, the governing equations might be, is really important to select are cases where you have kind of multiple physics happening at the same time. Because a lot of times, your engineering situation, it's not just a structural situation. It's not just a thermal one. It's not just a fluid one, right? You have multiple things going on at the same time. And I think the best example of this that I can think of actually came from a project for someone in this class too, was that they did a finite element simulation of a brake pad. And what they were interested in is, how much or will the brake pad actually deform as it's actually, trying to stop this vehicle. Okay. Which seems like, maybe a fairly straightforward thing, but, as a brake pad is kind of, pinching, the axle or the wheel, that there's going to be a ton of friction forces that are being applied there, right? And what does friction create? Friction creates heat, okay? And so what this person had to do was he had to do a combined structural and thermal simulation at the same time. Okay? And that heating is actually extremely important too, because, a lot of the material properties of any material, they depend strongly on temperature, right? And so we know that, if you take like a glass of water, if you have it at room temperature, it's going to have a certain density, it's going to have a certain viscosity. But then if you heat that up to boiling, the density is going to be different and the viscosity can be different. Right? Structural properties are the same thing, right? And so if you look at the Young's modulus or you look at the density of a material, it's going to depend on what temperature it is, right? And so, he wouldn't be able to get like an accurate simulation of this brake pad without taking that heating into account, because that temperature and that heat that comes from the friction actually really makes a big impact on how it's going to deform structurally. Okay? And so you kind of have this kind of like feedback loop where it's like you solve the structures, but then you solve the thermal, and then those kind of feed into each other as the simulation goes along. And so it's, it gets really interesting, it gets really complicated. And so, if you do have an engineering situation that you think multiple things are going to be happening, you can do that in finite elements. It's just you kind of have to explicitly kind of set that up. Because if you don't, then ANSYS is going to assume that there's only one thing going on. Okay, so any questions on this? Okay. All right, so that's part 2. And so the last component that I want to go over is the boundary conditions. Boundary condition, not boundary conditions. Okay, and so what boundary conditions do is they define, they basically specify how the solution is going to behave on the boundaries of your domain. Okay. Right, and so what the boundary conditions represent are they basically represents the influence of all external factors to your geometry. Okay. And so most commonly, the way that we think of boundary conditions, at least from a structural point of view, is we think of them as these are our loads and constraints, okay, or loads and supports. Okay. Because if you think about, where do those loads and constraints come from, right? Those come from external factors that are external to your geometry, right? So we think back to our plate, right? We applied a fixed support on one side of the plate, right? So that's the reason that that's fixed is because we basically super glued it or we welded it to something external to it, right? Same thing for the load, right? And so that tensile load that we're applying, you know, the only way that that came about was like someone was taking it and kind of pulling it like that, okay? And so any kind of external influence on your domain, you know, we represent that with a boundary condition, okay? Right, and boundary conditions are really important because without them, you know, actually your model actually won't really do anything, okay? And so a lot of people think of boundary conditions as kind of like the instigators or kind of like the inputs to a finite element simulation, okay? Okay. In a lot of ways, you know, a lot of people think of boundary conditions as, you know, the boundary conditions kind of initiate some kind of action, and then your domain will react to it. Okay. And the way that it reacts, that's governed by the governing equations. Okay. And so I'll give you an example, right? So you know, I'll do something that people on Zoom can see too. So if I took my stylus and just kind of held it like this, right? Like, you know, like this, it's just chilling. It's not really doing anything, right? It's not until I actually pull it and try to take it apart, you know, that's when things start to get really interesting, right? And so if I bend it, if I kind of push it, that's when stresses start to develop inside the pen, right? And so, you know, you can kind of think of it as saying that, you know, unless I actually do something to this pen, it's not actually going to be doing anything interesting, right? It's only when I try to, you know, break it or bend it, you know, that's when we would want to do a finite element simulation, because otherwise, you know, nothing interesting would be happening to it. Okay. And it's the same way with physical situations too. And so if we took our plate, you know, if we took our plate with the hole and we did nothing to it, it would just be a plate that was just, you know, just chilling there. It's not until we actually started applying boundary conditions, then that's when interesting stuff started to happen. Okay. And so you can't have a finite element simulation, or I just said you can't have an interesting finite element simulation without some boundary conditions of some kind. Okay. And actually ANSYS will actually stop you. So if you don't have enough boundary conditions to create something interesting, ANSYS will literally give you an error, say that this is the most boring thing I've ever seen. And then it'll ask you to apply more boundary conditions. Okay. It won't tell you like that. It'll tell you in a little bit of a nicer way, but you know, that's basically what it's telling you. Okay. All right. Any questions on this? Okay. All right. And so that's the three, you know, components of a boundary value problem. And so, you know, whenever you guys open up ANSYS to do any kind of project or any of the activities, you know, I want you guys to be thinking about, you know, how do I formulate this as a boundary value problem, right? So what's the domain? What's the governing equations? What's the boundary conditions, right? And so if you think of your engineering problems in terms of those three things, you know, then you know, applying it within finite elements becomes, you know, really, really easy. Okay? All right. And so the next thing I want to go over is the types of governing equations that, you know, that are common for finite elements. And of course, this is not an exhaustive list. You know, it's just kind of a list of kind of the three most common that you'll see, at least in ANSYS. But you know, I think it's kind of a good starting point. It's kind of good to kind of think of it in terms of this. All right. And so the first one I want to go over is the equations for linear elasticity. Okay. Let me clean this up a little bit. Okay. Linear elasticity. Okay. And so what these equations do is they determine how a solid object will deform in response to being externally loaded. Okay. All right. And so in case you were curious, you know, this is something that's just trivia. You know, I don't expect you to learn this equation, but in case you were curious of what the PDE for this looks like, it's basically an expression of Newton's second law, but just in terms of lots of, you know, scary partial derivatives. Okay. And so the equation looks like this. And so you have the divergence of the Cauchy stress plus a body force. This is equal to the density times the acceleration of a particle. Okay. Right, so you don't need to know this. You know, we're not going to go any deeper than this. But in case you're curious of what the equations look like, you know, this is what they are. And this row right here is density. Okay. And for linear elasticity in particular, what we assume here is that there's a linear relationship in between the Cauchy stress and the strain inside the material. Okay. Okay, so essentially we're assuming this. Okay. And in fact, this particular equation here is called Hooke's law. Okay. And so when you specify static structure with an ANSYS, you know, these are actually the equations that you're solving. And so you're actually solving the equations for linear elasticity. Okay. And so linear elasticity works great, usually when the deformations are pretty small. Okay. Because once you start getting into larger deformations, then the stress strain relationships kind of stops being linear. Okay. And so if we look at kind of a typical stress strain curve, so this is strain down here, and on the y-axis we have stress. Okay. We all know that there's a portion of the stress strain curve which is relatively linear like this, right? But then once we get past a certain amount of strain, then it starts to get, you know, a little bit different. Okay? And so linear deformation or linear elasticity basically assumes, or I would say it hopes, that you kind of stay within this region of the stress strain curve like this. Okay? Once you start to get outside of that, then you start to need to actually start to account for things like plasticity and plastic deformation. But for this class, you know, most of the time we'll be within that regime, and so, you know, we should be okay. Okay, so any questions on linear elasticity?
Yeah, that symbol next to the E for Hooke's law, is that epsilon?
Yes, that's epsilon. So this is the string right here.
Thank you.
Mm-hmm. Yep. Mm-hmm. Okay. All right, so that's the linear elastic equations, and so, you know, a lot of our structural problems we use that those equations. Okay. Next, we have heat transfer, or the thermal equations. Okay. And so the governing equation for this is the heat equation. Okay. I give big props to whoever came up with the heat equation and didn't have the narcissism to name it after himself. And so just calling it heat equation is great. And so it's not not named after like Newton or Navier or Stokes or anything like that. It's just heat equation. It's just very simple. It tells you everything you need to know. Okay. And so what the heat equation tells you is that these basically determine how heat and energy propagate through a medium, and you can solve it for the temperature distribution. Okay. Okay. And so the mathematical form, at least in its very compact form, is given by the following. Okay. And so we have K times the Laplacian of the temperature T is equal to Q, where Q is the heat generation, or thermal generation. Okay. And this K right here is the thermal conductivity of the material. And so if you're solving the heat equation within ANSYS, you need to specify what the thermal conductivity is going to be, because that's an important parameter for thermal. Okay. All right. And so we won't be working with thermal all that much, although I do have kind of a small worksheet or a small handout that shows you how to do it. But we're going to be focusing mostly on structural in this class. Okay. But in case you're interested in doing that for your final project, I do have some material. I do have some content that's for that. All right, and so the last one I want to go over, and probably the third most common, equation that you'll solve as a mechanical engineer, is for fluid flow. Okay. And so these equations determine how a fluid will flow inside a domain. Okay. And the governing equation for this is the Navier-Stokes equations. Okay. And so this is the only equation I didn't have to look up when I was writing these notes, is because I've written these so many times that I know it by heart now. Okay. And so, as you guys probably know, if you've taken fluids before, that Navier-Stokes is a nasty, nasty equation. And so, if you can solve this with finite elements, or, you can avoid solving this PDE, then, you're doing yourself a really big favor. Okay. Okay. Any questions on these? You're still writing down Navier-Stokes, bringing back bad memories. Hopefully not. I know some of you were in my fluids class last year. I'm not teaching fluids this year, so I'm a little bit sad. But but I got to teach this class in the fall, so that was kind of the trade-off. It was either teach finite elements or teach fluids, and so I chose finite elements. Yeah, that's true. I went with the flow. That's a good way to put it. Okay. And so we're almost done. We're almost done for today. And so we have 15 more minutes. And so I do want to take a brief look at, kind of that the kind of that thing that we talked about at the beginning of class today, where, you know, finite elements, what it does is it assembles this gigantic linear system. Okay, so I want to take a little bit of a closer look at that. Not too close though, because if we look any more closely, then we'd have to dedicate a few more class sessions to this. But you know, I just want to let you guys know what's going on there, and basically how the software is actually assembling this linear system. And so I call this section of the notes underneath the hood. Okay. Element stiffness matrices. Okay. And so this is kind of the equivalent of, you know, popping the hood of your car and looking up underneath the hood. Okay. And so you get to see kind of, you know, you get to kind of appreciate all of the fine engineering that goes on underneath. But, you know, similarly, if you pop the hood and just stare at your engine, you don't suddenly become an expert in automotive engineering. And so, you know, I'm not going to expect you to know any of the finer details of how this actually happens. I just kind of want you to be aware that these are the things that are happening. Okay. Because if we do get into these details, you know, again, it would be kind of a journey by itself. Actually, you know, we will get into it a little bit, you know, later in the semester, but in a very, very simplified form, strictly just for trusses. And so, you know, we'll be getting to it a little bit later on, but for now, you know, I just want you to be kind of aware of it. Okay. And so just to kind of refresh your memory, you know, the goal of finite elements is to make this. We have a gigantic linear system of equations, right? And so you have a gigantic matrix A, you have a gigantic solution vector X, and a gigantic right-hand side vector B, okay? Okay. And so the term for this linear system here, which is you know, this gigantic one, I like to call this the global linear system. Okay. All right. The reason it's global is because it's global for the entire mesh or for the entire problem. Okay. And that's different from, you know, the element stiffness matrices, which are kind of an element by element. Because actually, you know, all throughout today, you know, we've been talking about finite elements, you know, all of these kind of nice things about the theory in the background, but we haven't really talked about the elements themselves. Okay. Because remember, you know, a key part to our finite element analysis, a key part to our ANSYS is, you know, when we produce the mesh. Right? Okay. And so if you remember, you know, if we look at our kind of our plate with the hole, right? One key step here was that we broke up this geometry into a bunch of elements, right? Right. And so we kind of put like a waffle grid on top. Okay. And so how does these elements, right? So how do these elements actually contribute to a global kind of linear system like this, right? And so, you know, if we kind of color in each element kind of individually, right? I'm just coloring in some random ones for now, right? How do we go from this into something like a global linear system like that, right? And the way that we get there is that, you know, each element, you know, each individual element inside our mesh, what they're going to do is it's going to contribute a small part to the global linear system. Okay. Okay. And the way it does this is by computing its element stiffness matrices. Okay. All right, and so I'll show you how that works on the next page. So before I do that, are there any questions on this? Okay. All right. And so each element inside your mesh is going to contribute something called its element stiffness matrix. Okay. And so let's consider kind of an individual element in our mesh. Okay? And so, if we look at kind of, we kind of zoomed in on a particular element, we might have something that looks like this, right? And so this is a tiny element. Okay. And so from this element, what ANSYS is doing is that it's computing what's called the element stiffness matrix, which is kind of like a miniature version of the global linear system, but only for this element. Okay. And so the element stiffness system might be something like this, right? And so instead of a gigantic, maybe 10,000 or 100,000 by 100,000 matrix, we have this much smaller matrix called K. Right? And this K here is this is known as the element stiffness matrix, and it's a lot smaller than the global. Okay? Okay. And so for this example here, it might be something that's as small as like 4 by 4. Okay. Okay. And then this U right here is the element solution vector, and then the F here is the element forcing vector. Okay. And so I gave everything a superscript E to tell you that it's within the element. Okay. Right. And in case you're curious about how the element stiffness matrix is computed, it's computed from as a combination of what the governing equations are, as well as kind of the geometrical factors as well. So how big the element is, how skewed it is, how it's shaped. All of those are factored into how the element stiffness matrix is computed. But we're not going to get into that right now. It's going to be much later. But just know that that's how those are treated. Okay. All right. And so from here, we have this kind of very small system, right? Okay. And so if we look at our global linear system, okay, obviously, this one is much bigger because it accounts for all the elements or the entire our entire domain. Okay. And so what happens then is that, for this small system, it needs to find its place in the global linear system. Okay. And so it might only take like a small slice, like right there. Okay. And so what ANSYS is doing underneath the hood is that it's visiting, when you hit solve, what it does is it visits every single element in your mesh, and then it determines, what the element stiffness matrix is. And once it does that, then it slots it into the appropriate place in the global matrix. Okay. And then it does this for every single element. And so if you kind of combine all the elements together, okay, you might have something, that looks like this, where you have all these kind of patches where all the element stiffness matrices come in. Okay. You might have some that come in, maybe something like this. Okay. Okay. Right. And so you do that for every single element in your mesh, and eventually you're going to assemble this gigantic linear system that you can solve for your solution vectors. Okay. And then once you've assembled that global linear system, then you can solve it. Okay. And you can solve it using the computer algorithms that we talked about before. And then from there, that's what gives you your your solution. Okay. And so one factor that I want you guys to think about is that from this kind of explanation here, you can see that the more elements that you have, the longer it's going to take to assemble everything, just because there's more elements for the algorithm to visit. Okay. And so you kind of have this trade-off when you do finite elements that, if you include more elements, you're going to end up with a more accurate solution, but it's also going to increase the cost. And so it's going to take longer, it's going to take more memory to run your simulation. Okay? And part of the reason is because it's doing this thing. Okay, so any final questions on any of this today? Okay, so that's all I had planned for today, and so thank you guys for coming in. And so hopefully things went smoothly with the Zoom and in-person stuff too. So I plan to kind of continue this for the rest of the semester, and so you can come in virtually or come in person. I'll be here for both. Okay, and so have a great rest of your evening, everyone. I know a couple people wanted to talk to me about they had questions on their ANSYS activity, and so I'm going to stick around for that. But if not, you guys are free to go, and I'll see you guys on Thursday.
Thank you again, Dr. Trent. Just
I have no idea actually. So this is my first time in this room on Tuesday, but I'll stay in here as long as I can. And then if people come and kick us out, then they'll kick us out. But I'll stay here until they do.
Because I have a class after this. Is there anywhere else?
There's not a class. I know that they're going to because they were going to close it before we got in here.
Yeah, they've been really strict about that. So are you Kevin?
Kevin?
Oh, okay.
It's over until 10 or 11.
Oh, 10 on stuff like that.
Yeah.
Because I got good Wi-Fi the other day.
Okay.
When I was like, I had to zoom in with class when it was like 4, but
Yeah.
it was like second level stuff out of it.
Okay. Yeah, I might just do that then.
I know like some.
By the way, I'm so.
Oh, yeah. That's that assignment. Yeah.
On one day.
I know. It's more like.
It might be small, but it's like hours. Oh yeah.
I was kind of questioning. I was like,
No problem. Honestly, like I'm
That's a little crazy.
Okay, so as long as you're, not like.
Hi, dude.
Yeah.
Hey, I'll probably be on later.
I didn't even know. That's the best thing. Oh yeah. Oh yeah. Thank you so much.
Huh? Yeah, Thursday for sure, because there's part of the rocket team. Yeah, and so we are doing
About like the structural analysis of the
so I'm part of the airframe sub-team.
Part of what?
The airframe.
Oh, the airframe.
So like the body,
Yeah.
which includes like the fins and stuff. So they like.
So you just connect it to the tracks.
Yeah, so the fins have a shear strap on them when they're lifting because they're bolted into the frame.
Yeah, I mean that
Some are just glued on. Like my level 1 rocket is just
it's just glued on, but you're just like kind of staring at the hole.
But there's a funny thing that happens when you're rocking with a really high speed, close to like Mach 1 or anything like that. A rigid like fiberglass or carbon fiber or even steel thing can start to flutter. And it'll cause like actually a twisting motion as it's like if the body of the rocket and the pin here, it'll like twist it. They call it fin flutter, and it'll like shear it right off the rocket.
So it should depend on the speed of the rocket, something like that.
Yeah, so the faster it goes, the higher the stress is, yeah. Because usually rocket pins are symmetrical in shape and nothing's 100% perfect. So you're gonna get it kind of go over the side of it quicker in one direction than another, so it's gonna want to pull it. So it does this flutter thing. It can actually cause people to just rip right off of your rocket.
Probably have to make it as symmetric as possible with partners, like, you know.
It will reduce it, yeah, but there's still an added stress on there. And so that's one of the things that we have to calculate out for my design, but I mean, we'll see what FDA does to it. It will vertical stress from top down to the top of the pin to the bottom of the pin, or from a shear stress sideways.
It's like a horizontal.
Which would tell me like how much, how thick I would need to have the bottom bolted in so that it can resist that.
Oh, I see your point now. So it's like the thing like this, like a triangle, and then it's like this bottom needs to be thicker in order to.
Yeah. So the very, very tip of the pin, the very, very tiniest little triangle tip is gonna be skinny and narrow, but all the way at the base, it'll be like maybe thick as it sticks into it to resist that. Yeah. I don't know enough about it right now. I didn't even know it existed until like last year's senior design team was talking about it. I was like, what's a pin flutter? And he's like, oh, we got a bunch of stuff. It's a big deal. I'm like, okay. Yeah, neither did I. I thought it was cool. So Thursday, I'm bringing my rocket to school again.
Okay.
And because we had like a welcome fair out here like last week or something.
Yeah, I wasn't.
And so we were only there for a couple hours or something, but I brought it that day. And then my professor is like, hey, we have the provost of the university, basically like the second in command, who wants to walk around and take a tour of the engineering school and all of the senior design projects that are going on. So that includes like the Titan rover, the Formula One team, the Baja team, Titan Aero, the airplane, our Titan rocket, and a bunch of other stuff. So he's like, I need a few people from every team to like be there with stuff to show them. You know, he's only gonna be there for like 15 minutes, but he needs a really good impression so that, you know, they'll.
What time are you guys like?
Yeah.
This is Thursday around like 11:30 to 11:45.
And it's like the.
It'll be downstairs, just outside.
The engineering, like in front, like between engineering and computer science.
Yeah. So we have one of the buildings right next to this one, on the south side, yeah. We have like, I think they call it a power lab, but it's basically just the senior design lab. And it's like engineering E21, I think is what it is.
Oh, I see. It's like you have like some bunch of computers. I think I've been there.
Yeah, so we have like a separate little thing, and there's a bunch of computer stuff to use, like CAD software or whatever on. And then in the back, there's an actual shop with tools and stuff we can use. Anyways, he wants us to get in there and
So you guys are just showing it.
we're just like showing it off. He's like, we really need a good impression, so like, they're more adept to give us more money. Because we need more money for our project.
That's true.
But, yeah,
Good luck.
yeah. Is this your last year?
I'm actually a graduate.
You're a grad student.
Yeah.
You and who else?
And so I've been telling people that.
Jessica.
Usually also.
Jessica Arden's there. She's not in this much, she's in my combustion.
Make sure to ask her.
With Dr. Wang,
She's a graduate student.
and she's a grad student as well.
I didn't, I just not, I didn't know what it was.
Yeah.
Yeah.
I didn't know if like grad students take a lot of classes.
Yeah, we
together.
don't, just randomly take classes, and we do not like, I don't think there's like a graduate, like, kind of like gathering or stuff, we don't have such things.
That's too bad.
Yeah, I know.
Maybe it would help to have other people to study with, or, yeah. Of course, you guys might not even be studying the same stuff, so.
Yeah, exactly, so it's just, everyone's just going after the subject that they like, so.
Let's do this.
Did you finish your year?
So whenever you're.
I actually,
Where'd you?
from undergrad, I did not get here, it was not in engineering.
Oh, okay.
It was in chemistry.
Oh, okay.
Yeah, I'm having like a little bit of hard time sometimes.
It's not too
Yeah.
much of a stone's throw from that or whatever. Chemistry. is hard. I liked it. I thought it was fun.
I think it was like hard, it was hard for me too, it's just like quantum chemistry, so it was basically most like differential equations and stuff, but
Yeah,
like
yeah.
for atoms and molecules instead of. Yeah.
I have a friend who was here tonight, he was a chem major for his first year and realized he didn't like it very much. He's like, yeah, this isn't for me.
Yeah.
He's like, it takes a special person to do this stuff, so he's like, I'm gonna switch to engineering.
It's like, I like mostly computational chemistry, but it wasn't that popular in chemistry. Most chemists do not want to.
Not do the computations,
Yeah.
but yeah.
They just like, it's like you want to go to the lab, just make some things like
Every
that.
year.
But yeah,
Every year it's something I've never seen before. There you go. Yeah, and then also the details.
Yeah, we'll see you later.
Like VR, something, the virtual computer lab.
Yeah. So I'll say it's a little bit lighter. So basically what you're doing is you're accessing these computers. It's not a physical computer here, so you're not gonna hijack it. That's it runs on the same system.
Yeah, I didn't have that. So I thought, older stuff. So,
Yeah, probably the VCL probably. I think we're.
No, I haven't on my.
That's the VCL. That's something.
On my campus,
You're here,
Trying to
you're
get
here,
through,
yeah.
so.
Yeah.
But that's there.
I was just saying in this class.
Oh, so that would be perfect, I think so. The only thing here, the only thing. I don't think I know. Yes, just, let me close this. Yeah, I'm personally.
Problem that we did for the first worksheet.
What was that one?
It was kind of what we went over tonight with kind of like, what is the structure of, setting up lenses or whatever. And what is
Oh,
going
okay.
through, what are the three, or what are the three main things that relate to, solving or list the steps and procedures, whatever, what it is. What is under the hood was.
Oh,
like,
okay, yeah.
anything or whatever. I was like.
Yeah, yeah.
oh,
So after a combination of today and then the very first lecture, the lecture slides, I think that should give you.
Yeah, because I went through back to the first lecture slides, whatever, to answer that. Not realizing you have like.
So this is new. So I actually had that question before I had these notes, and people actually really struggled to answer that one. So
Yeah,
maybe I should actually say more specifically.
it's not
But yeah, it's not, it's, I mean, it wasn't hard to drive, but it was from just like that. So it was kind of. Wasn't too bad, I guess. So we see the. See the video. Probably for.
Oh, yeah, yeah.
You
yeah,
sit
I
right
mean,
next to your laptop. Hole?
that's, everyone yesterday said it was okay, but you know, every class thing.
Yeah, I was worried. I was like, well, if you had tech problems, I'm like, I had my laptop. And
I appreciate
I brought my
it.
webcam, and I know it's super sensitive, but I was like testing it out. And I'm like, well, I'm like across the room or, 6 feet from it or something like that. The audio can be sketchy or whatever. So like, I might just have to like put some laptop up.
Yeah, there's just no good way to do the whiteboard, which I'm sad about because I really like the whiteboard, but I think just right now it's just not practical.
Yeah.
I'll answer Chris's question later.